For our first step, we are going to move everything to one side of the equation. So we're going to add 4/5 to both sides here. So we've got our x plus 2 over x squared minus 9 plus 4/5 is greater than or equal to 0. Now we need a common denominator. And so we are going to take each of these fractions and multiply it by whatever it needs for its denominator. So this first fraction needs a 5, so we're going to multiply by 5 over 5. And the second fraction needs the entire x squared minus 9. Multiply top and bottom by the x squared minus 9. Okay, now we can distribute everything in the numerator. We have 5x plus 10 plus 4x squared minus 36. And that is all over the 5 times the x squared minus 9. All right, now we can just combine a couple of like terms here. The 10 and the minus 36 combine. And writing that in standard form, we've got 4x squared plus 5x minus 26. And that is divided by the 5 times the x squared minus 9. Now our goal here is to find the zeros of the numerator and denominator. That means we like everything factored, if possible. So I'm going to trust that we can kind of figure that out here, and I want to go through all the details there. So for that numerator, we get an x minus 2 and a 4x plus 13. And our denominator, that's a difference of squares there, so we've got our x minus 3 and our x plus 3. Okay, so now we've got our completely factored form, so we can find the zeros of the numerator. Set x minus 2 equal to 0 and 4x plus 13 equal to 0. That gives us x equals 2, and here if we subtract 13 and divide by 4, we get negative 13/4. And we find the zeros of the denominator as well. Set x minus 3 equal to 0 and x plus 3 equal to 0. And that gives us x equals 3 and x equals negative 3. We've got these 4 different numbers that we now need to draw on a number line. Okay, so we've got, let's see, negative 3, and a positive 3, and a positive 2, and negative 13/4, which is a little bit less than negative 3, actually. Now this is not to scale, and that's totally fine. All we really care about is the intervals that we have. Okay, so this breaks up our thing into 5 different sections. Okay, we want to label each of these also as either 0 or undefined. Okay, those that came from the numerator, which were these ones here, those are zeros. So when x is 2, we get 0. I'll just mark it underneath. And at negative 13/4, that's a 0. And the 3 and the negative 3, those were undefined because those came from the denominator. Okay, now we need to just plug in a number somewhere. I'm going to plug in 0 because 0 is a really easy number to plug in. Okay, and I'm going to plug it in right up here. It's going to be a little bit easier. And all I really care about is if this is positive or negative. And if I plug a 0 in here, I get negative 26 over here and negative 45. So a negative over a negative, which is positive. So I'm going to go ahead and mark that as positive, okay, when I plugged 0 in, which is, of course, between negative 3 and 2. And now, each one of these zeros, okay, those all had exponents of 1. So an odd multiplicity means that as I cross over that, I change signs. So from positive, I change to negative, and from, let's do that in red. From negative, I changed back to positive. And here, moving to the left, from positive, I changed to a negative, and from negative, I changed to a positive. Okay, and now we are looking for our solution where this rational function is greater than or equal to 0. So we're looking for positives and when it's equal to 0. So positives, we've got a positive right here. So that's from negative infinity up to this point here, which is negative 13/4. And at negative 13/4, it's equal to 0. So we're going to include that because our inequality was greater than or equal to 0. Okay, we also have this interval between -3 and 2. Okay, at -3 it's undefined, so I can't include that. But at 2 it's equal to 0, so we will include that because, again, we want greater than or equal to 0. And finally we have this last interval from 3 to the right forever to infinity. And at 3 it's undefined, so we can't include that. And of course we never include infinity. So this is our solution to that rational inequality.